What is a power series?
Coefficient times x to the power.
Coefficient times x to the power, good. And so when we write out terms of a power series, what kind of functions are we making? Polynomials. When I say, do you remember what the power series for 1 over 1 minus x looks like? X to the n. That's one that you memorize, right? That's like a parent power series. And so what that means is that, what does that mean? What if I were to graph 1 over 1 minus x and 1 plus x squared plus x to the third on the same set of axes? It's going to hug. The two functions are going to coincide, practically hug each other really tightly. But do they hug each other everywhere?
No,
Just on the interval of convergence. And only if you go out to infinity in your polynomial do they hug exactly. Everything else it just hugs pretty closely. But it only has a shot on the interval of convergence, which is what? -1 to 1. So let's just, again, because this is so important, look at what this looks like on a calculator. I am going to, well, don't look at that. That's cheating. Did you see it?
Kind of.
Okay, don't forget it. Forget
I
it.
forgot what it was like.
Okay, so don't look, just forget it. It didn't look pretty. What did it look like?
Nothing.
Nothing.
It was like air.
Okay, so I want to graph 1 over 1 minus x, which is what kind of function? It is a geometric power series, but this is a rational function. 1 over 1 minus x is a rational function. It's not a polynomial. Do you see that? This is not a polynomial, 1 over 1 minus x. But we were able to derive means like
Not differentiating.
to show something from something else. We were able to derive the power series. And the power series we said is x to the n. And what are the first 4 terms?
1 x squared.
1 plus x plus x squared plus x to the third. And we could keep going. But if we just graph that, we're going to get a cubic function that hugs our rational function between -1 and 1. Because it's between -1 and 1. Does that make sense? If it had a different interval of convergence, it would hug that other piece. But, how could we do a better job hugging our function?
Add more terms.
Add more terms. So we could do, what's the next term in that power series?
X to the 4.
X to the 4. Okay. And so what kind of function am I going to get now? A quartic. So it's no sort of like a quadratic form. What this also means is that if I pick a number in my interval of convergence, it should be pretty much the same if we plug it into the rational function or to the polynomial. Does that make sense? There is actually one place where it should be exactly the same. What is that? 0, where it's centered.
Oh.
Where the quartic is centered and where the function is, those should completely line up. Where is it centered?
1.
Look at where this polynomial is centered. At 0. It's centered at 0, between -1 and 1. And if I plug 1 over 1 minus 0 into my function, I get 1. If I do 1 plus 0 squared plus 0 to the third, I get 1. So in the center, they should match up perfectly. If I move off the center, are my function 1 over 1 minus x and the power series going to line up perfectly? Not perfectly, but pretty close, depending on how many terms I go off. So let's pick a number. Yes, because it's going to be centered differently. So let's pick a number in our interval of convergence, but not 0. Let's do something more interesting. 0.33. So let's not even do a 1 decimal number. Let's do 0.33. So if I do alpha y equals and do 1 over 1 minus 0.33, that's what I get. I want to, if I do 0.33, 1 plus x squared. I have to get pretty close to that. How can I get closer? Add another term. So plus 0.33 to the third. I get even closer. Plus 0.33 to the 4th. I'm going to get closer and closer and closer. So that's the idea of what we've done so far. If we look at what we've done so far, we started last unit in geometric with some geometric series. We did other types of series too, but just purely geometric series, like 1/2 to the n. You remember that? And then, yeah, so that one converges. We also looked at 3/4 to the n. Were those power series? What's the power series? Coefficient times x to the power. What were we missing in those? X. Yeah, those weren't polynomials. We were just adding up numbers, right? Now we're working with power series, and we're adding up terms. So we're adding up x plus x squared. We're adding up x's to a power. Is there some overlap between geometric series and power series? Yeah. 1/1 minus x is a geometric power series. Does that make sense? You multiply by x every time. And really, we have been living so far in here. We've been looking at power series that look like a/1 minus r. Does that make sense? Yeah. But there's this whole other world of power series that we have not looked at yet because they haven't been this intersection with geometric series. We are going to look at new types of series. Tomorrow I'll define what it is, but they're Taylor series, which is a subset of power series, and Maclaurin series, which is a subset of powers of Taylor series. What's his name?
I'm gonna change my name to that.
Okay, you should.
No. Really? Lauren. Lauren.
Okay, focus. My parents are going to listen to this on YouTube, and they're going to see that I can't control my class.
Dad was my orchestra stuff.
Okay. Okay, so we are going to get into Taylor series and Maclaurin series starting today and really going into tomorrow. So far, so I want to go through. We have found power series representations of functions related to a/1 minus r. Some functions that we found power series for: 1/1 minus x, x/1 minus 2x, x/2 plus 2x. Yes, these are all related to a/1 minus r. So we found power series for functions related to a/1 minus r. We've also been able to find the power series for arctangent x. Does that look like a/1 minus r? No, but what does? It's derivative. So we were able to anti-differentiate a geometric power series to get that. We've also found power series for functions like 1/1 minus x all squared. We had to anti-differentiate. Does that make sense? And then differentiate it back. So we've only worked with functions related to a/1 minus r. Today and tomorrow, we have the same goal, but with functions that have nothing to do with a/1 minus r, that are not geometric at all. Does that make sense? Our goal for today is to take cosine x and turn it into a power series. What's the power series? Coefficient times x to the power. So we want to turn it into something that looks like, that's my first coefficient, another coefficient times x, another coefficient times x squared. So the derivative of cosine is sine. So that is like,
That's like, oh, arc cosine.
That's what I was
oh, like arc cosine?
Like,
So actually, 1 over the square root of 1, wait, what is it? 1 over the square root of 1 minus x squared?
It's negative. I think it's
Yeah, negative 1 over the square root of 1 minus x squared. That doesn't look like a/1 minus r. Do you see that?
Yeah.
Well, you can turn it, you can make it.
Well, you can do it
steps and steps and steps.
I don't think so. But yeah, that's a good thought, but it doesn't look like a/1 minus r. It looks like a/1 minus r to the 1/2. And that's different. Do you know what I mean?
Oh, the root.
Because that square root, that's what's messing it up. But that's a really good thought. But do you see what our goal is? To turn cosine x equals some infinite series. And so if we graph cosine x and this power series, they should line up. But it doesn't look geometric, and that's our problem. Makes sense so far? Okay. What should be your thought when I tell you this?
How can we make it look like?
How can we do that? And then also your thought should be why. And so now we're going to get to why series are so cool. I really like, this is the why. I'll let you know. What is cosine of 0? 1. What's the cube root of 8?
2.
What's natural log of 1?
0.
What's e to the 1?
E.
E. This is easy. You know how to evaluate those functions. Does that make sense? You know how to do that. But what if instead what if instead, no, this is important, focus. What if instead I ask you what's cosine of 2?
We don't know yet.
What's the cube root of 2? I mean, cosine of 2, roughly what is it? This is what cosine of 1.7 is
Yeah, so it's
0. So it's like negative something. But you don't know negative what, right? Negative point something. What's the cube root of 2? What's natural log of 2?
E to whatever.
0.0.
Yeah, but then it keeps going, right? How do we figure out what it keeps going to? So what do all of you do?
Wait, there's 0.
You put it in the calculator, and your calculator gives you as many decimals as you want. How does your calculator know?
There's a little guy. It's smart.
There's a little guy in there? Okay, so there's a tiny little guy in there. And what that tiny little guy is doing is putting 2 into a polynomial, plugging 2 into a polynomial. So the idea is that if we can get cosine x to look like c0 plus c1x plus c2x squared plus c3x cubed. It's really hard for me to plug cosine to evaluate cosine of 2. But could I plug 2 into that polynomial? Could you square 2? Can you cube 2 and multiply it by some other rational number?
With everything that's irrational series.
Yeah, so you can. Everything that's irrational, you can approximate it with a series. And how accurate can you get?
Infinitely accurate.
Infinitely accurate, because you just go out far enough in your series. Does that make some sense?
Yeah.
That's how we get that we know that the square root of 2 is 1 point da 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 da, because we find a Taylor series for our square root function, and then it's just a polynomial, and we can get as accurate as we want in those decimal places by plugging into a simple polynomial. That's crazy. That's what the little man in your calculator is doing. He's just squaring and cubing stuff.
That's fun.
Isn't that cool? Okay, you should be excited by that. That makes me excited. But we want to figure out, well, we need a power series for cosine x. That's what we're looking for. We need a power series for cosine x. You don't have to write any of this down. You never have to do this again, but I want to show you where it comes from. Does cosine x look like a over 1 minus r? No. Neither does its derivative or antiderivative, or its inverse function, or the derivative of its inverse function. This has nothing to do with a over 1 minus r. But we want to find a power series because polynomials are really easy to work with and other stuff isn't. Polynomials are really easy to work with. So we know cosine x looks something like that. Or that's what we want it to look like. C0, coefficient 0, plus first coefficient times x, plus second coefficient times x squared, plus third coefficient times x to the third, and so on. If I want to, oh, this is the power series set at 0. Do you see that? I'm going to start by trying to solve for those coefficients. The only thing I'm missing are those coefficients, right? I have x and x squared and x cubed. I just need to know what's the coefficient in front on these polynomials. So I want to start by solving for c sub 0. What could I plug in for x to both sides of the equation to make everything go away except c sub 0?
0.
If I plug in 0, do you see that c sub 0 is going to stay, but every single term here has an x in it? So it's just going to go away. So let's do that. Let x equal 0. And then I get cosine of 0 equals c0. Do you see that? Which means c0 equals 1. So we found our first term.
Whoa.
That's great.
We're one step closer. How many terms do we have to go? Infinite. So we better get started.
Infinite ones.
Okay, so now we have to get a little bit more creative. As it says, now let's get creative. We know cosine x equals 1 plus the first coefficient times x plus the second coefficient times x squared, and so on. I want to figure out how to get x squared and above to go away, but keep the C1. Do you see that I can't plug in 0 anymore?
Factor out it. No, that wouldn't work.
Then you would still have it. So if you plug in 1, then I get cosine of 1, which I also don't know what that is, so that's not helpful. But I get 1 plus C1 plus C2 plus C3, so I have all these coefficients still. So what do I really need to plug in for x to make a lot of them go away? I have to plug in 0. But if I plug in 0 right now, C1 is going to go away. So how can I get the x away from the C1?
You can't factor it.
I can't factor it because then the x is still there.
You take the other side. Plug in 1.
So we just said if we plug in 1, I can't divide by x. That's a good thought. Dividing by x and factoring, x is 0, so I can't divide by it. Does that make sense?
Oh.
That's going to mess that up. So I want to figure out how do I get the C1 by itself? Well, then it's still going to be over there.
You can't do
And then when I plug in 0, it's going to go away. So I really need a way to get the C1 by itself. And then I want you to turn and tell your neighbor, what class are we in? Calculus. You can only do this with calculus.
differentiate.
You can differentiate both sides of the equation. Do you see that? This is cool. Don't say no. This is like my favorite thing to teach. So if you're sad, it makes me really sad. You don't have to write this down, but I want you to focus and to think. Let's differentiate both sides of the equation. It's not that hard. What's the derivative of cosine x? Negative sine x. What's the derivative of 1? 0. What's the derivative of c1x? C1. What's the derivative of c2x squared? 2c2x. So that still has an x on it, which is great. Does that make sense? And then it's 3c3x squared. That's what we get when we differentiate both sides.
So then you just
And now what can we plug in? 0. And everything's going to go away that has an x in it. And I just get that negative sine 0 equals C1. What is negative sine 0? 0. So then we get 1 plus 0x, which I'm just going to write for now. We'll take it out later. So there's no first degree term. Okay, let's keep going.
This is what the guy did in my video that you didn't watch.
Okay, it's on my to-do list. Okay, now I want to solve for what coefficient? I want to solve for C2, and right now I have 2C2x.
How do you? Oh, it's the derivative.
Because this is a derivative. That's what we have, and I went back to that first derivative that I have. What do you think I can do to get 2C2 by itself?
Differentiate.
Differentiate again. And so I'm going to get what on the left? Negative cosine x. And then I'm going to get 2C2 by itself. What am I going to get here? Which I'm going to write as 3 times 2C2, or 3 times 2C3, 4 times 3C4, n times n minus 1 Cn. What can you cancel?
Can you not?
Cancel 1. But I'm just bringing the powers down. And I get negative cosine x equals 2C2 plus 2 times 3C3 plus 3 times 4C4x squared, and so on. If I plug in 0, all these terms are going to go away. And I'm going to get negative cosine 0 equals 2C2, which means C2 equals what? Negative 1/2. That's what we have to see. I want you to try to find C3. So turn and talk to your partner. You don't really have to write it down. You can just look at it. But I want you to try to find C3.
It'll just be 0. So there'll be no odd.
Okay, so we're going to take the derivative of each side again. What do you get for C3? Sine 0. equals 6C3, which means C3 equals what? What do you think is going to happen every other term? Why? Because it's sine and you're plugging in 0. Do you see that? So we can already say that we don't have any odd powers in this. Because it's always going to flip back to sine. So it's going to go between positive and negative. So we already see that this series might be what? Alternating. But I want you to try to find this next one. This next one's not going to be 0. So keep going. And see if you can find C4. What's your coefficient on X right now? 2 times 3 times 4 C4. It's not just 4 C4. Because we've brought down our power how many times? We've brought down our power 4 times. Do you see that? So we brought down the 4th power, then the 3rd power, then the 2nd power, and now the 1st power. So what's C4? 124th. Which, how should you write 124th? 4 factorial. Because remember, going way back to the beginning of Unit 2, that factorial practice, what's the nth derivative of x to the n? N factorial. So what's happening is we take 4 derivatives, our 4th degree power becomes 4 factorial, and then we divide by it. Do you see that? What would happen if we went up another term, x to the 5th? What would our coefficient be? 0. And then we'd go up to our 6th. It'd be negative because it's going to alternate back, and it's going to be 1 over 6 factorial because we brought down 6, 5, 4, 3, 2 for our 6 derivatives. You see that? So this is what cosine x looks like. 1 plus 0x minus x squared over 2 plus 0x to the 3rd plus x to the 4th over 4 factorial. Yes, exactly. It could be 2 factorial. And it could be over 1 factorial on the first one. 1 factorial is just 1. So this is what it looks like. We're going to take out all those zeros because we don't need them. But I want to figure out, first of all, if we're going to write the general term, because we want to know, like, the general term of 1 over 1 minus x is x to the n. We want to know the general term for cosine. We know it's going to have what on it? An alternator, good, because it's alternating sine. So if this is n equals 0, n equals 1, n equals 2, n equals 3, and n equals 4. Let's just go through. We know it's alternating, and then it's a coefficient times x to a power. We need to figure out what the coefficient is and what the power is. What's the power going to be on the alternator? 2n. 2n would make it always even, which makes it always positive. N. So we want it to start what? Positive. So we need to start. No, we need it to start as, and we're going to start at 0. Oh. So we need it to be n. Does that make sense? If we're starting at 1, we need to start at n plus 1. But it's just going to be n. What's going to be
n plus 1.
My coefficient?
2n factorial.
2n factorial. We want all the even factorials. Does that make sense? We don't want odd numbers in there, just even. And what's power? 2n. So that's what cosine is. We have the power series. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And the general term is the alternator, negative 1 to the n, times x to the 2n over 2n factorial. You should write that down. This is the first thing that you need to write down. Should you ever have to do all that work again? No. This is a parent power series. You should remember this the way you remember the quadratic formula.
I don't remember.
Then remember it like you don't remember the quadratic formula. Wait, was I supposed to take the white ones?
You said the top one. You're still recording the sound.
It's okay.
She's doing drugs.
Okay.
Oh my, that was a lot, Lauren.
What happened?
I'm taking drugs for my headache. I'm not doing cocaine. I am drinking Coke.
You sure? You heard that, ladies and gentlemen.
I mean, it uses the same plant, so.
It does?
Yeah.
Click the link in our bio to donate to Miss Allen's.
Migraine fund.
In the description.
My bad, guys.
Come on. My
Wait,
bad.
is that why it's called coke? Because it's from the cocaine plant? I don't know.
Write this down.
The original.
It used to be.
What do you have on Monday?
Cocaine?
A pop quiz. One of your questions is, I'm just going to say cosine x equals, and you're going to write 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and then you're going to put plus dot dot dot, and then you're going to put equals sigma 0 to infinity negative 1 to the n x to the 2n over 2n factorial. That is question 1 of 4.
What are the other questions?
What's one of the other questions?
1 is
1 over 1 minus x, which is 1 plus x squared plus x to the 3rd, dot dot dot, equals sigma 0 to infinity x to the n. And then what do you think the other 2 questions are going to be? We're going to learn them tomorrow. Not natural log. It could be one, but it's not one.
Taylor series.
We're going to do sine tomorrow and e to the x. So those are your 4 parent function Taylor series. This is called a Taylor series. We'll define that tomorrow. It's a type of power series.
The guy who made it Taylor.
Okay. So now we can approximate the value of cosine of 2. This is cosine x. And so I just plug in 2 everywhere I see an x. Could you do that without a calculator? I mean, not you personally, but could people that have a lot of time on their hands do that without a calculator? Sure. I mean, that's just whole numbers. And then you have fractions, you turn them into decimals, and you could go out as far as you wanted. So before, I mean, this is what your calculator is doing. It's just people used to do this by hand to get approximations for cosine 2. I don't know.
No one has ever done it.
Wait, so realistically, this could all be wrong.
Yeah, 'cause it's all
No. So that's actually a really good
Everything's an
point.
approximation.
Because, okay, so let's just put cosine 2 in. Let's put cosine
It
2
won't
in.
give us infinite.
Yeah, I'm about to explain that. That's a really good point. I'm going to put cosine 2 into the calculator. And your calculator says it's that. That is correct out to this many decimal places. And how do they know? So you do 1. Ooh, what do I do? What's the next term? Minus 2 squared over 2. Plus what? 2 to the 4th over 4 factorial. Plus 2 to the 6th.
24.
Yeah, it's too bad.
That's 4 factorial. Over 6 factorial, which is 720. And I get that. Ah! Thank you. So that's pretty close to this, right? How can I be sure that this is, how can I get more accurate? More terms. And your calculator, actually, I don't know this is how your calculator works, but I'm just making it up. That's how it works. That's how we know. We can go out so far that our terms only change after 12 decimal places. Does that make sense? So if we go out, if we go out plus 2 to the 8th over 8 factorial, I actually sort of want to go out that far. Plus, let me delete this so we can start.
Why is it less?
Because it's alternating.
Oh,
Do you remember?
yeah.
When we thought about that one day?
We were doing the video and I was screaming at the phone there.
Okay, so let's just go out a bunch. Let's do a bunch of terms. Minus 2 to the 10th over 10.
You can do alpha window also.
Oh, thank you. Plus 2 to the 12th over 12 alpha window.
Alpha window 9.
Oh, nice. Over 12 factorial minus 2 to the 14th over 14 factorial. Look how close I am.
Whoa.
Wow.
Wow.
And so your calculator goes out far enough that adding another term won't change those 12 decimals. Does that make sense? And so that's how we can get it. How accurate can we get? infinitely accurate the more and more terms. And so your calculator knows that it only goes to 12 decimal places, so it's only going to go to as many terms that are necessary to get the first 12.
Like on your calculator, when it's like has like out the 12 decimal places,
Uh-huh.
and then like if you were to like subtract a number from that, it's only subtracting it from the 12 decimal places, right?
That's actually
out for
Catherine,
everyone.
I've never thought of that before.
That's fine.
Is that true?
I don't know. That's
I don't think so. Do you know when you get on your calculator like e to the negative 500?
It does.
I wonder, and I can't like answer this exactly, but I wonder if it's some combination of it's like rounding and then subtracting, and so it's not the actual value. Does that make sense? And so it's like practically zero, but not based on how your calculator is storing data. Because these irrational numbers, do they have the entire irrational number stored in the calculator? No, that's impossible. It goes on forever and ever and ever. So it rounds out to a certain place, and then it stops using the scalar polynomial. So
basically, all calculators are wrong.
I mean, what is cosine of 2? Does anyone know? No. Cosine of 2 is cosine of 2. It cannot be expressed as a finite decimal. How close can we get to the true value?
Infinitely close.
We can keep going forever and ever and ever. We can keep adding on to this polynomial. But that's how we get it. Is that not really cool?
That's all.
It's really, really cool.
Go down.
Okay, the only problem is that if I asked you what 1 over 1 minus 5 was and told you to plug 5 into your series, what would you yell at me? If we tried to plug 5 into 1 over 1 minus x, that series.
Not bigger.
Not in the interval of convergence, right? If I plug in 5 to both, that is not going to work. So what we just did was plugged in 2. Did it seem to work? So it looks like 2's in our interval of convergence, but we should probably know when this works and when it doesn't work. Does that make sense? So how do we figure out when it converges?
Cosine of x, then you can do
Ratio test.
Ratio test. You don't have to do it. I'll do it. But I do ratio test on that general term. So I look at the limit as I take the alternator off. X goes to 2n plus 2 over 2n plus 2 factorial times 2n factorial over x to the 2n. I can simplify. How many x squareds am I left with? X squared on top.
Yeah.
And what am I left with on the bottom?
2n plus 2.
2n plus 1 times 2n plus 2. So this is just ratio test. Now I take the limit as n goes to infinity. What does that limit go to? 0. So this is actually convergent for all real numbers, which is really, really cool. So you should add that to what you write down. I lied. On your pop quiz, you have one more thing you have to say, and that's that the interval of convergence is negative infinity to infinity.
I put all real numbers and not negative.
That's fine. All real numbers is fine.
Okay.
But the interval of convergence for the series is negative infinity to infinity. We can literally plug in whatever we want, and it should work. Oh, you already wrote this down. Just write the interval of convergence. So I want to show you now.
E to the x, because when you differentiate, oh yeah, you can, it's fine. Because you just get e there, 2 there, 2 there.
So it's actually going to be simpler because our coefficient is going to be. I mean, you can probably think about what your coefficient is going to be now.
Yeah. Wait. So just like, yeah.
It's just 1 over n factorial, but we'll get to that tomorrow. I want to show you what this looks like. So now I want to, just like we did before, we had 1 over 1 minus x, and we graphed this polynomial and saw that it laid on top of itself between -1 and 1. The same thing should happen if we do cosine x. So if I do cosine x, this is what you saw but you didn't see. Without looking at your paper, what's your first term?
1.
Then what? Minus all the even ones. Good. So x squared over 2 factorial, which is just 2, plus x to the 4th over,
Oh, I'm sorry.
plus x to the 4th over 24. Let's just start with that.
I like that.
Isn't that cool?
That's it.
Does it hug it from negative infinity to infinity? No. I had to go out a lot of terms for it to hug a lot of the interval. But yeah, so if I go back and add
Oscillating to a certain number.
minus x to the 6th over 720, do you see how it hugs better for farther?
Yeah.
And then if I go one more,
Is this what you
Do more.
forget?
yeah,
Can you go through 100?
and I can't type all that in.
Oh.
X to the 8th over 8 factorial.
One more.
I like that.
It's just gonna, the more terms I go, the farther out it comes.
From up and-
Yeah, so if I plug 2 in,
Oh wait, and because it's something it's gonna go.
if I plug 2 in to my red polynomial function, is it gonna be a pretty good approximation?
Yeah.
When am I gonna get a perfect approximation if I plug in what?
What?
If I plug in what for x, what x value
Oh,
gives me a perfect 0, where it's centered. They're literally lined up on the center and then they start to go off from each other immediately, but not very much. Does that make sense? If I try to plug in cosine of 10, or cosine of 9, that's right here. Is that gonna be a very good approximation? It's gonna be horrible. You see that? I'm gonna think that what's really negative 0.1 is like 10,000. What makes it bad?
You have to add more.
I have to add more terms. I have to add a lot of terms. I have to add so many terms if I want to plug in 9. What makes 9 bad but 2 good?
It's close to
It's
0.
close to the center. Good, Nelly. That is the point that we want to make. When you're approximating a function, you want to be as close to the center as possible. If you're far away from the center, that gives it more time to split off from the real function. Does that make sense? That's exactly right, Nelly. So, do you have some idea of why power series are useful?
Yes.
They are really cool because they're just polynomials that hug these functions. And you can write a power series for literally any function. And that's what we're going to talk about tomorrow. Taylor series is,
Art.
well, yeah, we already did that one.
Oh, oops.
But we could do it using the same method too, by differentiating over and over and over again. Cool. Any questions? You have no homework tonight other than to memorize this. Oh shoot, am I still recording? Yeah, I'm still recording. Yeah, so your only homework is to memorize this, memorize x to the n. We're gonna learn 2 more tomorrow and then do some things with them.
Like and subscribe.